Welcome to our module on data visualization and basic statistics, where we'll explore how to make data understandable. We'll focus on organizing, summarizing, and displaying data effectively to gain valuable insights and make informed decisions. Now, let's dive into the crucial topic of presenting data effectively for maximum impact and clarity. We'll explore why effective data presentation is so important and look at some common methods to achieve it. First, let's consider the immense importance of data visualization in today's data-driven world. Visualization makes even the most complex data much easier to grasp, simplifying intricate information for everyone. It helps us quickly identify important trends, discover hidden patterns, and spot any unusual outliers in our datasets. By presenting insights visually, data visualization significantly improves our decision-making process, leading to better outcomes. Furthermore, it dramatically enhances storytelling with data, making your reports and presentations much more compelling. Next, let's explore some of the most common and effective methods we use for presenting data. Tabular data, arranged in structured rows and columns, is ideal for presenting detailed numerical information clearly. Graphical data uses charts and graphs, which are perfect for quickly understanding overall patterns and relationships in your data. Using these effective techniques allows us to communicate complex insights very efficiently and clearly. Let's explore some of the key graphical visualization types that help us tell different data stories effectively. These visual tools are essential for crafting different data narratives, each suited for specific types of information. First, we have the bar chart, a versatile tool for comparing different categories using rectangular bars. Bar charts are excellent for comparing different categories, showing clear distinctions using varying bar lengths. Next, the line chart is particularly useful for visualizing how data changes over a period of time. Line charts are perfect for illustrating trends and patterns, helping us observe changes and growth over time. The pie chart is a familiar visualization that effectively displays proportions and percentages of a whole. Pie charts visually represent how each segment contributes to the overall total, showing parts of a whole. A histogram is crucial for understanding the distribution of numerical data within specific ranges or bins. Histograms effectively represent the frequency distribution of numerical data, showing how values are spread out. The scatter plot is invaluable for exploring the relationship between two different numerical variables. Scatter plots help us identify correlations and clusters by showing how two numerical variables interact with each other. Finally, the heat map uses color intensity to represent data, revealing patterns in large data sets. Heat maps are powerful for visualizing data intensity and patterns across a matrix using a spectrum of colors. Now, let's discuss some key guidelines for achieving truly effective data visualization in your work. These guidelines will help you create clear and accurate visual communications that convey your message effectively. Always choose the most appropriate chart type, as it directly depends on the kind of data you are presenting. Ensure you use clear and simple labels on your visualizations to enhance readability and understanding for your audience. It's crucial to avoid clutter. Keep your visualizations clean, concise, and focused on the main message. Select appropriate colors to clearly differentiate between various data categories, aiding quick interpretation. Finally, always ensure accuracy, as incorrect visualizations can severely mislead decision-making and understanding. Today, we're diving into the essential foundations of descriptive statistics, a crucial area for understanding data. Our goal is to learn how to effectively summarize and analyze the key characteristics of any dataset. First, we'll explore central tendency, which helps us find the typical value in our data. Central tendency identifies the middle point, or the most frequently occurring value within a given dataset. Next, we'll examine measures of dispersion, telling us about the spread of our data. These measures are crucial for showing the extent of spread or variability among the different data values. Then, we'll look at skewness, which describes the symmetry or asymmetry of data distribution. Skewness specifically indicates the degree of asymmetry, present in the overall distribution of your data. Finally, we'll cover correlation, which helps us understand relationships between variables. Correlation measures both the strength and the direction of the linear relationship between two distinct variables. Let's now explore some important statistical measures which are fundamental for data analysis. It's vital to understand these key formulae to perform effective and insightful data analysis. Our first measure is the arithmetic mean, commonly known as the average. The arithmetic mean, x bar, is the sum of all x sub I data points divided by the total number n. Here, x bar specifically represents the sample mean, which is our average value. X sub I denotes each individual data point within your given dataset. N stands for the total number of data points or observations in your sample. This formula provides the calculation of the average value for a set of data. It's found by summing all values and then dividing by the total count of observations. The arithmetic mean effectively represents the typical or central value in a dataset. Next, we have the variance calculation, a measure of data spread. Variance, sigma squared, is the sum of squared differences between each x sub I and the mean x bar divided by n. Here, sigma squared represents the population variance, indicating the spread of the entire population. X sub I refers to each individual data point in the population. X bar in this context denotes the population mean, the average of all population values, and n signifies the total number of observations in the entire population. Variance is crucial for quantifying the spread or dispersion of your data points. It is calculated as the average of the squared differences from the mean. This value clearly indicates how far individual data points are from the average. Following variance, we have the standard deviation, a more intuitive measure of spread. Standard deviation, sigma, is simply the square root of the variance, giving us the spread in the original units. Here, sigma represents the population standard deviation, showing data spread. X sub I again refers to each individual data point in the population. X bar remains the population mean, the average of all population values, and n still signifies the total number of observations in the population. Standard deviation is essential for measuring the overall variability within your data. It's simply calculated as the square root of the variance we just discussed. This provides a more interpretable measure of spread, expressed in the original data units. Finally, let's look at Pearson's correlation for understanding relationships between variables. The formula for Pearson's R involves comparing how x sub I and y sub I deviate from their respective means. R here stands for Pearson's correlation coefficient, indicating the linear relationship's strength. X sub I and y sub I are individual data points for the two variables, x and y. X bar and y bar represent the respective means of variables x and y. This coefficient quantifies the strength of a linear relationship between two variables. It measures precisely how strongly two variables are linearly related to each other. The value ranges from -1, indicating a perfect negative correlation, to +1 for a perfect positive correlation. Now, let's categorize data visualization diagrams to understand their diverse applications. We'll explore different diagram types, helping us choose the right visualization for varied data. First, we have statistical diagrams, ideal for numerical data. These are used for numerical data representation, often to compare or show distribution, including bar, line, pie, and scatter charts. Next are geometrical diagrams, focusing on spatial and structural relationships. These diagrams are used for spatial and structural representations, focusing on relationships and hierarchies, such as tree and Venn diagrams. Lastly, we have process flow diagrams, which illustrate sequences and workflows. These illustrate sequences, workflows, and decision-making processes, with flowcharts and Gantt charts being common examples. Let's walk through a typical online order processing flow, step by step. The process begins when a customer successfully places an order on the website. Next, the system automatically checks the inventory to confirm product availability. Once inventory is confirmed, the system proceeds to process the customer's payment. After successful payment, the order is prepared for shipment, including packaging and labeling. Finally, the prepared shipment is dispatched to the customer, completing the order delivery. All right, class, let's now bring everything together with a quick summary of our key learnings from this session. We'll focus on the most important takeaways, the key points you should definitely remember from our discussion today. Remember, data visualization is crucial for simplifying complex information, leading to clearer understanding and better decision-making. We also learned that various graphical methods, such as bar, line, and pie charts, each serve unique purposes. For effective visualization, always choose the right chart, ensure clear labels, and critically, avoid any unnecessary clutter. Descriptive statistics help us summarize data by looking at central tendency, dispersion, skewness, and correlation, which is very useful. Important statistical measures we covered include mean, variance, standard deviation, and of course, Pearson's correlation coefficient. Finally, remember that diagrams are broadly classified into statistical, geometrical, and process flow types for diverse applications.